Welcome to today's Explainer. We are diving straight into the sheer, brilliant chaos of chemical changes today. We're going to look at exactly how matter transforms all around us, whether that's the slow rusting of an old iron nail or the rapid digestion of the food you just ate. But before we get bogged down in formulas and numbers, check out this quote. Facts are not science, as the dictionary is not literature. I absolutely love this because it perfectly sets the stage for what we're doing today. We aren't here just to memorize a random boring list of chemical facts. No way. We're here to learn how to read the hidden language of the universe. We're learning to read the actual stories that elements tell when they interact with each other. So here's our roadmap for today. We'll start with spotting a reaction, move into the language of chemistry, tackle the balancing act, review the reaction lineup, and finally, look at everyday reactions. All right, part 1, spotting a reaction and finding those physical clues. Okay, put on your detective hats for a second. Let's say you mix two things together. How do you actually know when a chemical reaction has happened? I mean, how do you know it isn't just a simple physical change, like ice melting into water, but an actual fundamental shift where the identity of the initial substance has entirely changed? Well, the universe usually gives us some pretty massive hints. When you observe a change in state, a sudden shift in color, the evolution of a gas, bubbling or fizzing, or a totally spontaneous change in temperature, those are your 4 critical physical clues. When you see one or more of these happening, your inner detective should immediately go, aha, a chemical reaction is going down right now. And this right here is a perfect, brilliant illustration of what I mean. That dazzling white flame, that is a magnesium ribbon burning in air. It's so intense. The solid magnesium metal is reacting with oxygen in the air, releasing this massive amount of heat and light, and it's changing completely into a white powder called magnesium oxide. So we have state, temperature, and color, all completely changing right before our eyes. Moving right along to section 2, the language of chemistry, writing the suspect's MO. Look, scientists absolutely need a universal shorthand to record all these reactions. Writing out big, tedious sentences every single time, yeah, that just isn't going to cut it. Compare these two options. Up top, we have a really bulky word equation. Below that, we have a sleek, precise chemical equation. Instead of writing out magnesium plus oxygen, we just write Mg plus O2. And that arrow in the middle is absolutely crucial. It points from the reactants on the left, showing you the direction of the change, straight to the new products formed on the right, which is MgO. It's clean, it's elegant, and it tells you the exact story of what's happening. Okay, section 3, the balancing act. This is where we balance the chemical ledger. So this is kind of the mathematical heart of our explainer today. You need to think of chemistry like this incredibly strict financial ledger, where literally nothing can ever go missing. The foundation of all this is the law of conservation of mass. Mass can neither be created nor destroyed in a chemical reaction, ever. If you start with a certain number of atoms on the reactant side, you absolutely, unequivocally must end up with that exact same number of atoms on the product side. They're just rearranging themselves into new combinations. The total mass stays exactly the same. So how do we keep that ledger perfectly balanced? We use a systematic hit and trial method. Step 1 is the most important rule here. Draw boxes around each formula. You never ever alter the core chemical formulas inside those boxes. You can't just change H2O to H2O2 to make the math work, because congratulations, you just turned drinking water into hydrogen peroxide. Step 2, list out your atoms. Step 3, equalize them by adding coefficients, just regular whole numbers, outside those boxes. And finally, step 4, pop in those tiny letters to show the physical states: solid, liquid, gas, or aqueous for stuff dissolved in water. And here's what a perfectly balanced ledger actually looks like in action. We're tracking a reaction between zinc and sulfuric acid here. Notice how the left-hand side matches the right-hand side flawlessly. 1 zinc atom in, 1 out. 2 hydrogens in, 2 out. 1 sulfur, 4 oxygens. It is in perfect harmony. The equation is officially balanced. All right, section 4, the reaction lineup, the 5 archetypes of chemical behavior. Now that we've got the language and the math down, let's categorize the usual suspects in our chemical investigations. We're going to start with the first 2 archetypes, which are, quite literally, exact opposites of one another. In a combination reaction, two or more things combine to form a single new product. Think of burning coal, where carbon and oxygen merge together into carbon dioxide. Conversely, a decomposition reaction is where a single reactant breaks apart into simpler products, like when you heat limestone up and it fractures into quicklime and carbon dioxide gas. They just mirror each other perfectly. Now, to force that kind of decomposition breakup, you always need energy. Sometimes it's just heat, but sometimes, like with the electrolysis of water we're looking at here, it's electricity. By running an electrical current right through the water, we're literally tearing those H2O molecules apart, forcing them to decompose back into separate hydrogen and oxygen gases.
Next up in the lineup is the displacement reaction. Imagine dropping shiny iron nails into a bright blue copper sulfate solution. Now, iron is highly reactive, a lot more so than copper. So the iron essentially acts like a bully, pushing the copper out of the way, stealing the sulfate to form iron sulfates, and just leaving the copper behind. And you can literally see it happening. The solution goes from this vibrant blue to a really faded pale green.
Then we step it up to the double displacement reaction. If single displacement is a bully stealing a partner, double displacement is a literal partner swap between two entire compounds. They just exchange ions. And the biggest clue that this has happened? It almost always creates an insoluble solid substance that literally falls out of the liquid solution. We call that solid a precipitate. Our final archetype brings us to oxidation and reduction, or as we usually call them, redox reactions. Notice how that copper powder is being heated over the burner? It's actually gaining oxygen from the air, forming this dark black coating of copper-2 oxide. It has been oxidized. But here is the real trick. Oxidation and reduction always go hand in hand. While one substance is gaining oxygen, or losing hydrogen, another substance is simultaneously being reduced by losing oxygen or gaining hydrogen. It's just this continuous, beautifully balanced chemical dance. Finally, Section 5. Everyday reactions. Chemistry in the real world. Let's bring all this abstract, theoretical chemistry back down to reality for a second, because these exact reaction types are heavily impacting our daily lives right now. Think about the slow, really destructive power of oxidation. It causes corrosion, which is exactly why the iron on our bridges rusts over time, and why silver tarnishes. But it also causes rancidity. When the fats and oils in our food oxidize, they spoil, changing completely in smell and taste. It's literally the reason why your potato chips go bad. That's why food manufacturers have to use chemistry to fight back. They add antioxidants, use airtight containers, and they even flush chip bags with pure nitrogen gas just to keep the oxygen out. But hey, it's not all just rust and bad potato chips. Right this very second, inside every single cell of your body, an incredibly complex web of chemical reactions is keeping you going. Respiration itself is an exothermic reaction, meaning it releases energy, as it breaks down glucose with oxygen to give you the energy you need to just sit here and watch this explainer. So I want to leave you with this thought. Respiration is just one reaction. What other hidden, perfectly balanced chemical equations are running inside your own body, keeping you alive right now? Thanks so much for joining me today, and keep exploring the reactions all around you.